Welcome to our 6th lectures on fax devices. Today we shall discuss closed loop control of the fax devices. To discuss it, we shall first actually discuss about the simplest DC to DC converter, that is buck converter, and its different control technique. So since our understanding of the buck converter is quite familiar, for this I have chosen this to discuss. Thereafter, this concept of the closed loop control will be actually used in our fax devices also. So, essentially a buck converter with the voltage mode control can be used to stabilize with the proportional and the PI gain of the compensator, that we are familiar with it. And but problem lies, we require to have few more aspects like short circuit protection, stability, which can be done better with the current mode control. For this reason, however, we have a high performance for the more sophisticated compensation network is required, especially multi-layer ceramic capacitor is used. And on the other hand, to stabilize the DC to DC converter with MLC, the capacitor require more attention compared to the stabilizing the converter for the electrolytic one. And depending on the size and the type of the component, output filter are used and switching frequency, bandwidth, etc. is determined. Whatever I am telling for the DC to DC converter, same thing applicable for the fax devices also. Let us consider the operation of the voltage mode control of the simple buck converter. So, this is the devices, and that contains the parasitics. This RL is actually parasitic resistance associated with the R, and this is ESR, and ultimately these will actually lead to the some kind of deviation from the actual work, and we require to stabilize its output. Generally what we do, we have this is actually noise subtractor, noise suppressor, and we require to scaling down, and ultimately you require to fit the scaled output voltage, and this is going to compare with the V reference, and V reference is generally made from the input side with the help of the Zener, and then we put a PI controller. Task of the PI controller, you know that actually to eliminate the actually steady state error. Now what essentially it does, and how you will actually calculate the value of this R and C, and sometime we will put a proportional resistor to it. So, what happened here, this value R and C will gives you the bandwidth. You can write actually Kp plus Ki by S, it can be rewritten K plus 1 plus Kp by Ki into S, and you can write K into 1 by Ti by S. Now this Ti you should require to match with this value of the RC network, and generally it should be you have to choose the op amp with the proper bandwidth, and whatever may be the switching frequency of this sawtooth wave, generally Ti is considered around 10 times or 20 times depending on the practical application into it. And this will actually operate this this is a synchronous buck converter. So, to reduce the losses of it, since when MOSFET is on, it is only RD on, so losses will be very much minimized. For this reason we use a synchronous buck converter nowadays instead of the normal buck converter, and this is the way actually it works. What is the disadvantage of it? Disadvantage of it, definitely it is not short circuit protection free. Whenever actually if there is a drags very huge amount of load, and it actually try to regulate the voltage only, and it does not take any information about the current. For this reason we require to put extra circuitry to control or the limit to the current protection. But this scheme can be further modified. This is actually the voltage mode control. This scheme comprises of an error amplifier. This is consisting of an error amplifier, and a PWM modulator and a LC filter, and this compensation network contains at least one pole and two zeros to cope up with the second order pole of the LC filter, and the ultimate goal being to obtain the closed loop transfer function equal to a first order system. Ultimately it will be a order reduction, and since a first order system inherently actually damped, so you get a damping effect of it. So, for this reason, to work it in a finite manner, in a stable we require at least one pole and two zeros. These are the requirement for the working with the from the stability point of view for the voltage mode control. Now, this is the principle of operation of voltage mode control. You got VREF, thereafter you can compare with it, and this is basically the control structures. All this PI controller has been incorporated here, and thereafter you will have a sawtooth wave, and in sawtooth wave will actually give you the pulses, and that pulse will run this MOSFET. Now, there are few consideration while actually considering the closed loop operations of the voltage mode control. The zero crossover frequency or F0, usually the frequency is chosen as 1/10 or 1/5 of the switching frequency. Why I have explained? Because it is a concept of bandwidth, because what a PI controller actually do, it will eliminate the steady state error. We expect that within the 10th of the cycle, within actually 10 cycles or 5 cycle, the error will be eliminated, steady state error will be eliminated. The compensation time is determined by location of the zero crossover frequency and characteristics of the output capacitor. But unfortunately, the output capacitor's value actually it is not very much known to us. There is actually some degree of unknown, because value of ESR changes with the frequency and also load condition. So, thus we require to take a guess something, and we require to, while designing, we have to keep in mind few things. This is a compensation type, and where you see that this is actually the resistance of the ESR, and where it required to be greater than FLC, and FLC is required to be actually should be, again it should be actually less than the cutoff frequency of this PI controller, and that should be at least more than twice of the switching frequency as prescribed by the Nyquist criteria. Similarly, if you take a type 3 a PID controller, then this is the logic. Now, you have FLC actually is less than F0, and here this ESR frequency of this ESR should be greater than F0, and same condition will get it from the A. And if you choose a type B PID controller, I am coming next what is type A and type B type PID controller. So, you will find that FLC actually is less than F0 and less than F by 2, and at last ESR value will come. Depending on the value of the ESR frequency for different combinations of the capacitor, we require to choose a particular type of the PID or the PI controller. So, see that this is a type 1, this is a PI controller. So, this is normal PI controller of type 1, type 2. So, here you can find it out, this is a normal PI controller, and here this capacitor put into the picture, and thus it has an effect on the control system. Let us go back to the previous slide and see that what is a type 1 and type 2. In type 2, actually you require FLC is less than FLC should be less than FESR and less than this cutoff frequency, and thereafter it should be less than of the switching frequency. So, this is the case, and this is the type 3 type of circuits. And this is basically a PID controller. Now, this constraint in design can be simplified by using a current mode control, where there will be a outer loop to compensate voltage, and there will be a fast acting inner current loop that will give you a reduction of order of the stability, and also it will take a corrective action very fast. Moreover, inherently, since it is a current control, it will give a short circuit protection. So, let us see the different block diagram of the current control. This part is same, this is basically you can replace it any type of PI controller which has been already explained you. So, this is basically the outer voltage loop, this is basically the outer voltage loop, and thereafter you have a compensation network, and from there you get a scaled value of the error here, and you got a V ramp, and ultimately you measure the current value with a filter which will eliminate the high frequency noise, and it will compare, it will add up, and ultimately it will be totally compared with the ramp, and accordingly frequency will be generated. So, here this part of it is a inner loop for the current, and other is the outer loop for the current. Let us see how does it work, very simple way. This part was same in case of the voltage mode controller, where PI controllers and all the scaling has been put into the block HB, and thereafter you will be sensing the current. It can be sensed by a resistance with very low value of inductance, or by a Hall effect sensor, and that you put it, and ultimately you will have a comparison. So, you are allowed to current to grow, and once this actually you have a scaling network, and accordingly you require to scale it. So, it will be compared. So, when you have a voltage error, current is allowed to grow, and thus voltage will build up. When there is no voltage error, then actually then the output of the comparator will be 0, and thus it will come down. And this is the principle of operation. Ultimately you have a scaled value of Vc. So, once it touch Vc, it will come down, and accordingly it will generate pulses. There are two kind of current mode control. One is called peak current mode control, other is called average current mode control, and it can be operated in fixed frequency as well as a variable frequency. So, this is a peak current mode control. Whenever it touches some value of the peak current, generally it is put by a limiter, and that is depend on the switch rating and other devices that puts restriction on it. So, then you will get a clock pulse, and you will generate the PWM, and this is a peak current mode control. This is constant on time control, where frequency will change, but the value of this actually T on will be constant, and this is the constant frequency control. In this case, value of the T on and T off will vary, but frequency will same, and similarly you can have constant off time control. Now, we can have a hysteresis control, that is a simple control, and that is very frequently used for our fax devices applications. So, generally to avoid chattering, we generate a band of plus minus, and actually current is required to oscillate between this band. If it actually put to the higher band, then it then actually the switch which is transferring power will be off for the buck converter. Ultimately current will come down through the diode. Here diode been replaced by the MOSFETs, again it will carry on. So, this is called a hysteresis controller. Hysteresis controller has a great usage in case of the fax devices also. especially in STATCOMs. So, see that current mode control here, here is actually the upper voltage loop, outer voltage loop, and this is basically the inner current loop. So, what does it do, you know? So, this put an information and ultimately this operate this small switch, and once this switch is operated, accordingly actually current will pass and will be measured, and this is basically the concept of the multi-phase buck converter. You know, if you require to increase the power density of the MOSFET, power density of the converter, then generally we use this kind of concept called multi-phase buck converter, where actually 3 buck converter or multiple buck converter is connected in the same output DC bus voltage and same input DC bus voltage. So, since you do not allow to off that much of time because of the huge amount of current required to flow, for where actually for this kind of thing is very much suitable for low voltage high power applications, and these are what happened is most of the cases this carrier wave was phase shifted by some angle to accommodate it. If there is a 2 such thing, there are 180-degree phase shift. If there is actually multiple of it, and accordingly it will be phase shifted. Now, current regulated PWM. This is very important for our drives and the effects point of view. Since the flux and the control torque output of the AC motor is directly controlled by the current, and same principle in used for the STATCOM for DQ based technique. So, current based PWM control has been put to use for the fax devices. Now, what you have generally a current control with the output voltage through a voltage FET converter. So, it is voltage control. So, it is current control voltage source inverter essentially put into use. Feedback current will be used to control the machine's currents in case of the drives applications, and for the fax devices for the actually for the STATCOM current. And you know, we have 2 kind of PWM technique for the current control, that is instantaneous current mode control and hysteresis band current control. Now, this is instantaneous current control. You have this I reference which is AC, but why we discuss DC here, you know, actually there is a STATCOM operation can be done in DQ frame, where this quantity actually will be treated as AC, and thus you know it can be also the same principle what has been used for the simple DC to DC converter can simply be extrapolated for those applications when we are actually convert this ABC frame to DQ frame. But anyway, here let us consider that you have a AC reference and you are controlling the hysteresis loop. Here you are controlling the instantaneous current. So, what happened? You are basically maybe actually injecting the current in case of the STATCOM. So, you have the I reference, and ultimately this is the I actual it has been sent back to you, and there will be a little phase difference phi, and that required to be eliminated. Ultimately you compare it and you put it to the PI controller, you generate actually a signal for the SPWM or different kind of signal. For this actually for this active power filter you may have this kind of peaky kind of signal. This will be the reference, and you have to track this reference. Essentially for the shunt active power filter you have actually the harmonic contents of 5th, 7th, 11th, 13th. So, you have this kind of reference and it has to track that reference, not necessarily all the cases. This will be sinusoidal, and that value will be fed to generate PWM in case of the instantaneous current control. Now, what are the advantage of it? Here actual current I is compared with the command current I star, and the error is fed to the PI controller. The rest of the circuit is a standard PWM topology of the 3-phase inverter, and same control is used for the other 2 legs, and for the 3-phase 3-wire system generally we leave one leg actually to be controlled accordingly. Although the control approach is simple, this method produces significant phase lag, which I pointed out. There is a delay in estimation, and of course the delay can be compensated by a control circuits by a lead compensator, but designing a lead compensator also will be difficult because this delay is not constant. At high frequency, which are the very harmful for the high frequency drives as well as the STATCOM application. So, instead of that we use hysteresis band current control, that is more actually popular for its simplicity, but problem is that there is a disadvantage of it, will come little later. So, hysteresis band current control, the actual current tracks and the command within the hysteresis band, which I have just shown few slides ago. In this approach, sign or other reference of the current is compared to the actual phase current. The current exits the prescribed hysteresis band, the upper switch in the half bridge is turned off and the lower switch is turned on, and when it is crosses the lower limit, then the reverse applications happens. The current goes below the hysteresis band, and the opposite switches are being put into the application. This kind of band is called actually constant band PWM. There is a different kind of band, it is an algebraic band PWM. We may have also proportional band PWM. So, this is sine wave. So, this is the lower band and this is the upper band. So, let us discuss about the constant band PWM, which it can be, you can generate a band by an op amp very simply. So, essentially let us consider a 2-level inverter. So, actually this is the switching of it, and once it hits the upper leg, so correspondingly the lower leg will be on and ultimately you will get the lower voltage, and once it is dropped and hits the lower band and upper leg will be on. It is quite similar to the PWM sine triangle PWM, which has been already seen. You can see that this actually width are quite big in duration in middle to reciprocate the area of the sine curve, and it is almost same of the sine triangle PWM. But problem lies the frequency of this current is not constant, it is variable. So, designing filter for it is little painstaking. So, let us analyze it. So, L didt equal to VDC minus V sin omega t. So, essentially this is the for actually the voltage of half bridge VDC minus the common mode voltage V sin omega t. Now, what we can find, we can actually reduce these equations, and since sin omega t is varying, thus L didt is varying. Since you have, we can assume that del, you can rewrite this equation as del I by del t, and del t you can think of as actually 1 by del t you can think of about the frequency. Since value of del I is constant, we can say that frequency is varying. So, what happened here? V sin omega t opposing the load current and L effective of the inductance. Similarly, in the lower switch, this is the equation, it is basically minus point Vd minus Vm sin omega t by L. So, there are few things we require to keep in mind. why this frequency varies. So, we can write 1 by del t as f equal to this 0.05 Vd minus Vcm sin omega t by L into del I. So, what happened here? You can see the frequency is maximum when V sin omega t is 0 and it is minimum at the peak. So, you will find that as you can see this waveform, here frequency is more, here frequency is more, and here frequency is less. So, one of the disadvantage of it, it is not a constant frequency operation. For designing the filter for it, it is painstaking. So, let us see that what happened here. Peak to peak current ripple and the switching frequency are related to the width of the band. Of course, because it is a ramp side, ramp will be taken on that much of time. Select width of the hysteresis band to optimally balance the harmonic ripple and the converter switching losses. That is very important thing we have to keep in mind. And current control is easy, at low speed, but in high speed, since it's encounter high value of EMF, current tracking will be more difficult. But since our particular cases, we have a 50-year supply, it works excellently. Apart from the pain we require to put it for designing the filter. So, now let us see that how you design it. This is, I told you that it can be generated by the simple an op amp. So, this is an op amp in a positive feedback, thus it works in a hysteresis manner, and this is the actually the hysteresis loop, and ultimately from the lookout time Td, upper and the lower switches will be on. This is the very simplest implementations of hysteresis control. Now, how you can generate this actually hysteresis band? You can actually take the ratio. So, this ratio will be R2 by R1 plus R2. It can be 1%, it can be 5%, or optimally you can turn it on depending on the switches. And when upper switch is on, when it is low, goes to the upper circuit, and when minus HB, it goes to the lower switch should be on. So, in this approach, because this approach is very popular because it is very simple to implementation, first transient response, there is no phase delay and direct limiting of the peak current, and for this reason it is very frequently used, and there is a smaller decelerating voltage because of its fast action. However, that is a disadvantage of it. Like the PWM, sine triangle PWM, it is not a constant frequency operation, which leads to the harmonic ripples of the machines as well as the selecting harmonic elimination, all those things, and can be overcome by adaptive hysteresis band, where actually value of del I will change according to the back EMF or the actually point of common coupling of PCC in case of the STATCOM. And also significant phase lag at high frequency, that is not at all a constraint for our fax devices, but for the high frequency application this has been a constraint. Okay, thank you.